One eternity later, 3 days later, 12 seconds.
Okay, well, I'm back here, and after the break, I was able to try and refigure out what was going on with figuring out what the distance that's traveled of an accelerating object. So I had to go back and search and find out what the formula is for calculating distance based on acceleration. Okay, so I found it. This is the equation here. So it's basically 1/2 times the acceleration times the amount of time which passed squared. So in order to figure this out for our simple scenario where we have 1 kilogram of being accelerated with 1 Newton for 1 second, you would put in 1/2 times 1 meters per second times 1 second squared. And if we do that, we come up with half a meter. Okay, so this is how far a 1 kilogram weight accelerated by 1 Newton force will get after 1 second. It will only be able to get half a meter, not of the meter that I was originally thinking. So we can now plug this into our formulas to see whether the energy is conserved. So the original formula is work equals distance times the force. So the distance is half a meter, not a meter now, times the force, which is 1 Newtons, which means it's 0.5 joules. All right, so this is the amount of energy we put into the rocket to get it to go for 1 full second, right? So does this equal the 1/2 mv squared formula? However, this is the trick. So we plug our numbers back in. So 1/2 times the mass is 1 kilogram times the velocity, and it does in fact equal now. Okay, so phew. Okay, the amount of energy does appear to be conserved, right? So we don't have to worry about this over unity situation where we get more energy out than necessary. No, we get the amount exactly the same amount of energy out in kinetic energy as we got putting in using a rocket. All right. So let's go under the more complex scenario where we got like a 3 kilogram object going under a 13 Newton thrust. And what do we do here? So first we have to calculate what the velocity is going to be of a 3 kilogram object undergoing a 13 Newton thrust for 1 second. So if it was 1 kilogram, then it would have been 13 meters per second if we're doing 13 Newtons. But since it's 3, we have to divide it by 3. So it should actually be 4.33 meters per second after 1 second of a 13 Newton thrust, right? So that's how fast it should be going after 1 second. So we have to then calculate how far would that object travel. So we have 1/2 times the acceleration, which is 4.333, times the amount of time, which is only going to be 1 second. So in 1 second, it should be able to get 2.166 meters. So if we calculate the work, then we come out with 2.166 meters times the force of 13 meters, which equals 28.16 joules. Okay, so that's the amount of amount of energy in joules being put into the rocket to fire it for 1 second. Okay, so let's see what happens to the kinetic energy formula. So that's going to be 1/2 times the mass, which is 3 kilograms, times the velocity, which we believe is going to be 4.33 meters per second after 1 second. And indeed, after I punched in all the numbers, magically, it ended up being the same. So even in this more complicated scenario, the formula 1/2 mv squared seems to work. So sorry, DraftScience is like, it looks like 1/2 mv squared actually works when I'm doing this little test to see whether energy is conserved. So, but there's this question of, why does this formula work? And I just dug this up on the internet, and what's the 1/2 doing in there, and what's the t squared doing in there? Did they just drop those in there arbitrarily? So the thing is that it's not intuitively obvious, but if you're trying to figure out the distance of something traveled, typically you would do that by just taking the constant velocity, like that's something going 5 meters per second, you would just multiply that by the amount of time that goes by. So if it was going 5 meters per second and you let it go for 2 seconds, it's like the distance traveled is 10. But what do you do when it's not a constant speed, when it's accelerating from, like, 5 meters per second to 10 meters per second, right? How do you calculate that? That seemed to be something you need calculus for. But the mathematicians tell me that all you have to do is just average those two speeds, the beginning speed and the ending speed. You average them, and you can use that to calculate the distance instead, believe it or not. So if I had something going from accelerating from 5 meters per second to 10 meters per second, I just have to average the speed. So 5 plus 10 divided by 2 is 7.5. And if I let it go for 1 second, it would travel 7.5 meters, right? Hard to believe. But, you could theoretically test this. For example, gravity is 9.8 meters per second. And since you're starting with a zero velocity, then the average of zero plus anything is half. So So this is where the 1/2 actually comes from, because your starting velocity is zero. So zero plus, say, 9.8 meters divided by 2, the average is, 4.9, or it's going to be like 16 meters. So you could test this by taking a rock, go up 16 meters and drop it. And if this formula is correct, it should take exactly 1 second for it to do that. And you could calculate how far it can drop for, say, 2 seconds, and go find a higher place and see whether it takes the 2 seconds for that to drop, just to see whether this hard to believe formula, actually works. But presuming that it does, that is where the 1/2 comes from. It's not arbitrary. It's that you're averaging two values, one of which is zero. So now you're probably also wondering, where is this time squared thing coming from, right? I'm always get tired of it. Okay, so the thing is that the distance traveled is going to be the velocity times the time, right? We just first discussed that, right? But in this case, to figure out the average velocity here, we have to take the acceleration times the amount of time that is happening, and then we have to divide that by 2 to get the average. So we have actually time in here twice. So if we go and rewrite this here, we get the 1/2 times the acceleration times time squared, right? So that's where the time squared comes from. So I hope that kind of gives you some intuition as to, how to calculate the distance, and why is it that the distance that something can travel while accelerating is actually 1/2 the acceleration, right? Because you're just averaging, and that's where the 1/2 comes from. And that is why that works. So, from this standpoint of trying to do a energy balance between something that can create that velocity and the eventual velocity, it seems that 1/2 mv squared works. But no, this could still all be some gigantic conspiracy to make me believe this, because they just want us to believe that. It'd be much more convincing that if we could come up with an experiment where, like, fire a gun and you measure the velocity, and then have some way of actually measuring what that actual energy is, so that we're not relying on all these other formulas. How do I know that work is actually force in newtons times distance, right? It just works out that way. So that's why all the scientists believe it, because that's what they've been told. But it'd be more convincing if, then they fired a bullet at, twice the velocity, and showed that the actual energy, maybe it could knock down more stuff or something. It actually increases in that way, since the velocity squared does considerably change the value of the energy. So I'd like to see that. But much to the credit of DraftScience, he's done his own experiment. So before we ended this, I wanted to go take a look at his experiment briefly here. And let's see. So this is air track video here. So I think that's kind of clever the way he's got this set up. So what I do in this experiment is I look to see this black band, which is very clear against his ruler here. And I look to see when it exactly matches, say, one of the marks here. So this black band is exactly matching this larger tick here. And it seems that for every frame here, it moves exactly one tick. So after one frame, it seems to have moved one tick. So that's a very convenient measure. So he's trying to either confirm or deny that when these two things collide together, that this one is going to go in the opposite direction at about a third of the velocity, and then this larger one, which is twice as big, is going to go forward at 2/3. So we can go ahead and
for them to make contact with.
Watch them collide together.
Nothing hits the track; it's all in air.
You can verify that and, it's going one tick at a time.
There's a spring on each cart.
The other cart there.
Kind of obviously.
So there it goes.
And so the little pieces of plastic guarantee they have a good contact. And it's very light, so I didn't really worry too much about.
Now it's going apart. So now we got to kind of measure how far it's going apart. So we need to wait for it to exactly match. So it's exactly matching this back tick here, and it goes
much and all of that. So I can't guarantee the weights, but I'd say they're within 5.
So it takes about 4 ticks for it now to move 4 frames for it to move 1 tick. So there it looks like it's going back about a quarter of the speed backwards, and then forwards
5%.
You gotta wait for it to
1 mass to
right
2
there.
mass.
And let's see, you gotta wait for
now the numbers I got on this particular video were
so there it looks like it's almost at least 3/4 of the way from a tick from frame to frame. So it looks like he's getting maybe a quarter backwards and 3/4 forwards. So that's kind of close to 1/3 and 2/3, I suppose. If you're baking, it's probably be close enough. But it's an interesting experiment. I'm not sure it's enough to show that the kinetic energy formula should be MV. But and I think that I actually did experiments like this in the physics class in high school. So maybe he wants to buddy up with someone in the junior physics lab or high school, so he could play around with these actual air skate thingies, and not have to deal with trying to make stuff up on your own. But which again, I think that's pretty cool what he's doing there. But I think I would have to conclude, though, in total that the mainstream formula of energy equals 1/2 mv squared, it does seem to work. I mean, based on the initial calculations I did, if you account for momentum being a vector and they cancel, then it's like, yeah, they equal. So I'm not quite sure why no one else pointed that out to you, but that seemed to be fairly clear. And that even from a perspective of doing it a completely different way, which is to try and see whether the amount of energy input to an object being accelerated to a certain velocity is in fact equal to the kinetic energy, that seems to work out as well. So, and I'm kind of glad it worked out because, I was thinking that, yeah, this is totally settled science, and some of my theories, like, how do they derive mc squared, are actually dependent on that being equivalent to the kinetic energy formula, 1/2 mv squared. I mean, that's why they're the same. And if there wasn't, then, well, that would really kind of mess up that whole explanation. So I'm glad that it still seems to be 1/2 mv squared, but I'd still like to see an experiment where they actually physically measure the, say, energy of an impact and show me that it is 1/2 mv squared and not anything else. It's not, it should be fairly easy to show the difference between mv, which is just momentum, versus mv squared, right? So that's all I have for this video. And till next time, ta-ta.